For a brief moment in early 2026, something subtle but intriguing began to take shape in the data. Reports of bright meteor fireballs, those sudden intense streaks of light that briefly outshine the stars, appeared to be arriving with unusual frequency. Individually, none of these events were extraordinary. Fireballs occur every day somewhere over Earth. But the timing raised a question that was difficult to ignore. The apparent uptick coincided with the recent passage of our planet near the trajectory of an interstellar object known as 3I Atlas. Discovered as the third confirmed visitor from beyond our solar system, 3I Atlas immediately drew attention for its origin alone. Unlike typical comets bound to the Sun, its path traced back to interstellar space, carrying with it material formed under conditions entirely separate from those that shaped our own planetary system. Observatories across Earth and in orbit began tracking it closely, measuring its brightness, its motion, and the composition of the gas streaming from its surface. But as those observations accumulated, a more speculative question began to emerge, one that linked the distant object to events unfolding much closer to home. The idea, explored by astrophysicist Avi Loeb, was not that Earth had come close to colliding with the object itself. At its nearest, our planet remained tens of millions of kilometers away from 3I Atlas, an immense distance by human standards. But in astronomical terms, proximity is relative. Comets are not singular, compact bodies in isolation. They are dynamic systems, shedding material continuously as solar radiation heats their surfaces. Gas erupts outward, carrying dust and sometimes larger fragments into space, forming vast plumes that can stretch for hundreds of thousands of kilometers. Over time, that material disperses, spreading into diffuse streams that follow similar orbital paths. If 3I Atlas had been releasing debris during its journey, and there was strong evidence that it was, then the question becomes one of timing and motion. Could any of that material, once ejected, travel across space in such a way that it intersected Earth's orbit, just as our planet passed nearby? The physics does not immediately rule it out. In fact, under certain conditions, it allows for it. The key variable is velocity. Material ejected from a comet does not move arbitrarily fast. Its speed depends on the forces driving it outward, typically gas pressure from sublimating ice. If fragments were expelled recently, they would need to travel at speeds of several kilometers per second to cover the distance in time to reach Earth. That is on the higher end of what natural processes can produce, but not impossible. More interesting, however, is the alternative scenario. If the debris had been released years earlier, long before the object approached the inner solar system, then the required velocity drops dramatically to a few hundred meters per second. That range falls comfortably within known cometary behavior. Under that framework, the hypothesis begins to take shape. A stream of particles, gradually expanding outward from 3I Atlas, could, in principle, drift into Earth's path. The planet would not need to encounter the object itself. It would only need to pass through a region of space where that material had dispersed. And when it did, the result would look familiar: particles entering the atmosphere at high speed, heating up and producing streaks of light, meteors, and occasionally brighter fireballs. What gives the idea weight is not just that it is possible, but that it could happen at scale. Estimates of the object's total mass suggest that even a modest fraction, breaking apart into smaller fragments, would produce an enormous number of particles. If only 10% of that mass fragmented into centimeter-sized pieces, the resulting count could reach into the trillions. Spread over a vast volume of space, most of those particles would never encounter Earth. But a small fraction might, and even a tiny fraction of a trillion is still a very large number. From that perspective, the appearance of additional fireballs does not require an extraordinary chain of events. It requires only a modest overlap between Earth's orbit and a sufficiently populated debris field. The sky, in this view, becomes a sampling instrument, briefly intersecting a stream of material left behind by an object that originated light years away. If the story ended there, 3I Atlas would still be noteworthy as a rare interstellar object. But what has drawn increasing attention is not just where it came from or what it might have left behind, but what it appears to be made of. As more detailed observations were conducted, researchers began to analyze the composition of the gas surrounding the object. Within those measurements, one signal stood out with unusual clarity: an unexpectedly high abundance of deuterium. Deuterium is a form of hydrogen, distinguished by the presence of an extra neutron in its nucleus. Chemically, it behaves similarly to ordinary hydrogen, but its relative abundance carries important information about the environment in which it formed. In the universe, deuterium was produced primarily in the moments following the Big Bang, and since then it has been gradually destroyed inside stars. As a result, the ratio of deuterium to hydrogen varies depending on location and history. In our solar system, that ratio has been measured in multiple contexts, from Earth's oceans to the ice of comets. While there is variation, it tends to fall within a relatively narrow range. The measurements associated with 3I Atlas do not fit neatly within that range. Instead, they suggest a level of deuterium enrichment significantly higher than what is typically observed in solar system bodies. Such enrichment is not impossible, but it points to formation under extremely cold conditions, temperatures low enough to favor the incorporation of deuterium into molecules at elevated rates. These are environments found far from stars in the coldest regions of interstellar space, where chemistry proceeds slowly and selectively over long timescales. If those measurements are accurate, they imply that 3I Atlas formed in a setting very different from the one that produced the planets and comets we are familiar with. It may have originated in the outer reaches of another stellar system, or perhaps even in a dense molecular cloud, before being incorporated into a system at all. In either case, it represents material that has experienced a thermal and chemical history unlike anything commonly sampled within our own cosmic neighborhood. Unlike the fireball hypothesis, the deuterium signal is rooted in observational data. It is something that can be measured, refined, and compared across independent studies. And while the interpretation of that data may evolve, the anomaly itself demands explanation. It shifts the conversation from speculative interaction to empirical difference. Even if no debris from 3I Atlas ever reached Earth, the object would still stand out as chemically unusual. Beyond composition, additional observations have added layers to that sense of difference. Some relate to the balance of gases detected in the object's coma. Typical comets within our solar system are dominated by water vapor as their primary volatile component. In the case of 3I Atlas, there are indications that other compounds, such as carbon dioxide, may play a more prominent role than expected. This does not defy physical laws, but it does suggest a composition that diverges from the norm established by familiar examples. Other anomalies are more subtle, emerging from the way light interacts with the material surrounding the object. Measurements of polarization, the orientation of light waves after scattering, have produced values that are uncommon among known comets. Such results can reflect differences in particle size, shape, or surface structure. They do not point to a single clear conclusion, but they contribute to a pattern in which multiple independent observations fail to align neatly with expectations. There are also questions related to the object's trajectory. Its path through the solar system appears to align more closely with the plane in which the planets orbit than might be expected for a randomly incoming interstellar object. Statistically, such alignments are unlikely, though not impossible. Given a large enough number of incoming objects over time, some will exhibit trajectories that appear coincidental. The challenge lies in determining whether this particular case falls within that statistical tail, or whether it reflects something more systematic. Additional reports have highlighted unusual detections of certain elements in the gas surrounding the object, including instances where metals appear in vapor form under conditions that are not easily explained. In some cases, expected accompanying elements are absent or present at lower levels than anticipated. These observations remain under discussion, with alternative explanations being explored and debated. Taken together, these anomalies do not converge on a single definitive interpretation. Each one, in isolation, can potentially be explained within the framework of natural processes. Interstellar objects are expected to be diverse, shaped by environments and histories that differ from our own. It would not be surprising for such an object to challenge assumptions derived from a limited sample of solar system bodies. What has drawn attention, however, is the accumulation of these differences. When multiple independent properties, composition, optical behavior, trajectory, each deviate from expectation, the object begins to resist easy classification. It occupies a space that is neither clearly understood nor easily dismissed. It is at this point that the conversation becomes more contentious. In exploring these anomalies, Loeb has raised the possibility, carefully framed but nonetheless provocative, that some features of 3I Atlas could be consistent with non-natural origins. This suggestion does not assert that the object is artificial, nor does it provide evidence that it is. Rather, it extends the analysis beyond conventional explanations, asking whether all observed properties can be fully accounted for within known physics and natural formation scenarios. Within the broader scientific community, this line of reasoning is met with skepticism. The prevailing view is that unusual observations should first be examined in the context of incomplete knowledge rather than extraordinary hypotheses. Interstellar objects represent a new category of observation, with only a handful identified so far. Drawing broad conclusions from such a limited sample carries inherent risk. What appears anomalous today may become typical as more examples are discovered. This tension reflects a deeper aspect of scientific inquiry. Progress often begins with anomalies, observations that do not fit existing models. But not all anomalies lead to paradigm shifts. Many are resolved through refinement of measurement, improved understanding of underlying processes, or the discovery of previously unrecognized variables. The challenge is to distinguish between signals that point to fundamentally new phenomena and those that reflect the limits of current data. In the case of 3I Atlas, that distinction has not yet been made. The object sits at the intersection of curiosity and caution, offering hints of difference without delivering definitive answers. Its passage through the solar system is temporary, but the data it provides will continue to be analyzed long after it has moved beyond the reach of our instruments. What remains is a layered narrative. At its outermost level, there is the possibility that debris from a distant object briefly intersected Earth's path, producing a subtle increase in fireballs that flickered across the sky. Beneath that lies a more solid foundation, a chemical signature that suggests formation in an environment colder and perhaps older than those typically associated with known comets. And beneath that, a collection of anomalies that, taken together, resist simple explanation but do not yet demand extraordinary ones. The significance of 3I Atlas may ultimately lie not in any single claim, but in the way it expands the range of what is considered possible. Each new interstellar object adds to a growing dataset, gradually revealing the diversity of material that exists beyond our solar system. With each observation, models are tested, adjusted, and sometimes overturned. Whether the recent fireballs were connected to it or not may eventually be resolved through careful analysis. Whether its chemical composition represents an extreme but natural variation or something more unusual will depend on further measurements and comparisons. And whether its anomalies point toward new physics, new environments, or simply new examples remains an open question.